Okay, let's get started. So thanks everyone for joining today for our topical meeting on GNNs for tracking. First, we have Markus Atkinson from UIUC, who's going to talk about GNN tracking, graph construction, and network architectures. So go ahead, Markus. Thank you for presenting.
Thank you, Savannah. Let me mute that real fast. Okay. So I'll go over kind of the where we're at as far as optimizing the current GNN models, and then we will have a second talk after this that will go over kind of the hardware status, like progress with putting these in FPGAs and things. So the basic procedure for the GNN is we divide the processing phase into essentially three phases. We have what we call the pre-processing phase, which is graph construction phase, where we're going to use the hit coordinates within the detector to create the nodes in the graph, and then apply a series of cuts, both geometric and some truth level cuts, in order to reduce the size of the graph and choose which edges are going to connect the nodes. And then we also have explored a lot of other types of tricks in the graph construction phase to see if we can augment the data in different ways to get better results with the GNN performance and the tracking. The second phase after the graph construction, of course, is the graph neural network itself. So you can you want to process your graph through the graph network, train it, inference it, do all that, and then the last phase is, of course, the post-processing, where you take the results that come out of your GNN and attempt to build tracks, which you could use for calculating track parameters or for seeding, like tracklet algorithms. So all the work I'm presenting today is using the TrackML dataset, and this is an open experiment, and it's agnostic, and it has a score functionality that allows you to compare progress against different models. We haven't used the score functionality much yet ourselves, but we plan to in the future. So there's many places to improve and innovate here. There's lots of improvements to be made in the graph construction phase. We've started diving into this a bit, and then there's many different GNN architectures to explore. We'll go over a few of them today. And then the tracking work, because it's kind of the back end, is very preliminary. So we have some tracking results to show, but they're very much work in progress. So we'll move on to graph construction and go into a bit more detail here. So for the graph construction, we contribute to the ExtraTrackX codebase, and this is a NumPy-based data class, essentially. And this essentially uses a graph building algorithm known as layer pairs, where it forms edges between adjacent layers. One of the things that we have added since joining there is we added the ability to include the end caps, because ExtraTrack is very focused on the barrel only. And then we've also added, we had to add some new cuts to deal specifically with the end caps, because there's some nuances with the end caps that don't come up with the barrel. And then we looked into these data augmentation tricks, and we found one that seems very helpful, which we'll go over. And then this has been the ExtraTrack code. We have also fully converted it to a PyTorch geometric data set. And one of the goals that we want to do is essentially convert all of our code into PyTorch geometric, so that we can get everything into one working framework for easy comparing between the different models and stuff. But unfortunately not fully there yet. There's a couple of things that are not converted over yet. Some useful quantities when talking about graphs is the edge efficiency. So this is essentially, of all the true edges that could have made it into the graph, which ones actually did. So depending on the cuts you choose, you can, lose edges like that you would want. And then there's the edge purity, which is just what fraction of the edges in the graph are true versus false. And you can see that these are functions of PT. The track efficiency is pretty high. It's usually 97%. There's this dip at this low 0.5 PT cut, and this was just because the phi slope cut was not optimized at that point in time. And then the let's see, the fraction, the purity gets very pure as you increase the PT cut, and you end up with essentially almost purely already inferred graphs that are kind of trivial to solve. So the nodes, so the way we cut the nodes out, the biggest way to do this is just by choosing which layers you even include in the graph. So we tend to focus mostly on the inner detector, which has the 4 inner barrel layers, and then there's 7 end cap layers per side. We also have an ADA-based cut, which removes nodes. And then for nodes, we do have some truth-based cuts. So the reason we use the truth-based cuts is essentially to give us control over the size and the complexity of the graph. So one of the things that these do is they will remove noise hits. So some of the hits don't have a particle ID associated with them, and so these just get wiped out immediately. A feature I would like to include is the ability to keep these in the graph, but they're currently ignored. And then we have PT-based cuts on all the nodes, so we can just select those. And another way of removing nodes that I was not aware of is that the extratract code is actually removing duplicate hits within the same layer. So when you do the layer pairs approach, it only allows 1 hit per layer per particle. And this means that when you get your unions are going to be essentially like, if you have 3 points, they'll just have 3 nicely connected points. You won't have any sort of triangles and square shapes that start to show up. And so that's very useful for the layer pairs approach. And then for the edge cuts, we have 2 modes that we can run the layers pairs, which is essentially just allowing adjacent layers to connect. And then we have this layer pairs plus, which allows edges within the same layer to connect and form. And in this case, you would want the duplicate hits from the particle within the same layer. So this is a much more complex graph. And so we haven't explored a lot with the layer pairs plus. So most everything I'm going to show is using the layer pairs algorithm. We have these geometric cuts. So between any 2 points, you can essentially fit a line, and you can measure the slope and the intercept of that line and cut on those. And these are essentially the distributions of true edges and false edges. And you'll see that true edges tend to pile up down in the bottom left corner. They have smaller Z0 and lower phi slopes, and false edges are kind of uniformly scattered all over. So you can make these cuts really tight and really hone in on the true edges. But from some exploration, I found that actually made tracking worse. The tracking benefits from having some bad edges to help it learn, which is the reason why the Z0 is actually just increased to this arbitrarily large number, is to allow lots of bad hits in, which actually helps it train. And then we have to remove edges that intersect intermediate barrel layers when you connect the barrel to end cap. So like if you allow this bottom barrel layer to connect to this inner end cap layer, you can potentially get edges that pass through the barrel layers above it. And so this is something that only happens when you start including end caps. And so we had to add special cuts in to deal with that. And then, so the last thing we've really looked at is the data augmentation. And so you can augment the data after constructing the graph in various ways. So 2 ways that we do this that seem to help is, one is to just split the graph into smaller sections to reduce size. And this helps with the ability to put it inside an FPGA in the future. And then another data augmentation trick we found is if you actually reflect all the graphs through the phi angle. So just make a copy of the graph with phi equals negative phi. And this is effectively creating charge conjugate versions of the graphs because it's going to it's going to invert the handedness of the tracks. And this greatly helped the training. We also tried reflecting across like Z and some other types of transforms, which, I mean, they definitely affect the training, but they, didn't help. But the phi reflections seem to be pretty significant. And then the last consideration, which I briefly mentioned with graphs, is just the graph size. So while selecting cuts to try and maximize performance, this usually comes at the cost of increasing the graph size drastically, which makes it harder to accelerate on FPGA. So we're now starting to consider ways of reducing the graph size without losing as much efficiency and things. So one way you could do this is like, do we really need all 7 NCAP layers? Or could we get away with just like the NR4 or 5? Can we get away with skipping intermediate layers within the barrel? Different things like this are things we want to explore. Moving on to the GNN architectures themselves. So we have 3 that we've looked at. We'll probably looked at 4, but I'll talk about 3 today. We have a couple of edge classifiers. So we have edge classifier 1, and this is a entirely feed-forward network. The graph modules, a graph module is a combination of an edge network and a node network, and these essentially just do edge convolutions and node convolutions. This network has roughly 100,000 parameters. It is 6 graph modules with 128 hidden dimensions, and it uses a BCE loss, and a learning rate of 0.001. We haven't done a lot with this particular edge classifier, so I don't have a lot of results to show, but I just mentioned that we do have this edge classifier, and we are in the process of converting it into the PyTorch geometric data class. So we should be able to start comparing numbers that we get out of this to the other stuff very soon. We also have edge classifier 2, which is the largest network that we've used. This is a recursively connected graph modules, and this allows for aggregation of more distant information, and the weights can be shared. This model has about 260,000 parameters, so it's very large, and it's again 6 graph modules, 64 hidden dimensions. This though is probably our most optimized graph, or GNN. So all the optimizations we've made for the graph construction were essentially ran through the edge classifier 2, and so this one's the most optimized, which is why you're going to see the best results in the confusion matrix here of about 99.9%. And that's the edge. Those are edge classifications, not tracks. And then the third model that we've really looked into is this interaction network. And it's similar, but instead of edge and node networks, you have these relational networks and these object networks. And the big difference here is that essentially two nodes in the graph can have multiple relations between them. So you can have effectively multiple different types of edges between the same 2 nodes. And so that's one of the cool things with the interaction network. All of the networks are fully connected networks. And this one has total parameters of about 90,000, which is the smallest network architecture that we're currently considering or currently looking at. And then this one has about a 95% edge efficiency. And we can see that we can look at the amount of true and false, true positive, false negatives, false positive, true negatives as a function of the discriminant cut. And you can see the counts of the different segments and how they get split. So we'll move on to some tracking. So I will, before I go in the union find, I will just mention we do have some very preliminary results using dbScan tracking algorithms, but I was not able to find the slides. So I don't have the results, but we do have the ability to do a dbScan version of tracking. And then we also have the union find version of tracking, which we've recently overhauled into the PyTorch geometric kind of structure. And so the numbers I'm showing are pretty new. So so we use the union find, and we can run on the inferred edges, and we can just group these into the selected subsets. We can define a number. So we're looking for triplets here, but you can essentially look for, any size union you can define as a track candidate. So I just require there be at least 3 nodes in the union. But I have looked at like doublets and things as well. And then truth information. So one of the things that was modified when we converted the graph construction code into the PyTorch geometric dataset is we added a lot of truth information into the dataset itself. This truth information is not used by the network in training, but it is used by track matching algorithms for producing tracking efficiencies and things. And the matching criteria, therefore, is just all hits in the same union are from the same particle. And that's how we define a match currently. So the track efficiency is defined as the number of matched track candidates divided by the total number of truth tracks. The truth information that comes with the graph is for the full detector. So even if you use, only the inner detector, it will show you all the hits for the full detector, even the duplicate hits in the layers. So you have a full list of hits for every particle, and then you can calculate essentially what is a total global tracking efficiency. So if you simply just don't even include the end caps at all, you're going to lose 30% of your tracking efficiency right there because you're not including 30% of the detector. And then the fake fraction is defined as the unmatched track candidates over the total track candidates. So one of the cool things is you can run this directly on the target graphs. And what this will allow you to do is quantify like the best case scenario you could possibly get if you had a perfect GNN. So the tracking efficiency number that will come out when you do this is essentially the maximum track efficiency you could get with the current selection of graph cuts that you've chosen. And then your fake fraction should always come out as 0 by construction. And then when you run it on the inference graphs, you'll get the tracking efficiency for the particular GNN combined with the graph cuts. So it's going to be a total efficiency loss due to both graph construction and GNN inference. And you're going to get the fake fraction for that particular GNN architecture. And then if you ratio these, you can essentially get the fraction of unions that are inferenced correctly, which is a useful number for kind of categorizing the GNN itself. So then we can answer at least some of those questions I posed, which is like, how many end cap layers do you really need? Do you need all 7 end cap layers on each side? So you can see that if there's no end cap layers and you only use the barrel, the maximum tracking efficiency you can kind of hope for is about 60%. And then as you include more and more barrel layer or end cap layers, this goes up and it approaches 94% if you have all 7. But I don't know, I think you could probably get away with like 5. Take the 1% drop in efficiency because you'll probably reduce the graph size by like 30% or something. And then the GNN ratio, is 0.99. So these are, again, all from Edge Classifier 2, and this is our most optimized model. So we're getting 99.9%. I'm not sure exactly what to call this, but it's like tracking the GNN's ability to preserve tracks, I guess. 99% of the tracks are preserved. And then another thing you could ask is like do you gain stuff by including more barrel layers? So there's a 60% roughly that you can get with just the inner barrel. And then if you look at the full barrel, it only goes up to maybe 63%. So, you know, because it's the same kind of region of the detector. So you don't gain that many more tracks. And then the alternating barrel is essentially, it's the full barrel, but I'm only using every other layer. I'm using the innermost of the alternating layers. And then you'll see like this comes with a drop in tracking efficiency. So, and also a drop in the ratio. So the GNN struggles more with the alternating barrel than the full barrel. And then I also tried running, because I was removing layers, I tried removing layers in the actual definition of a track candidate. So instead of triplets, I allowed for doublets, and this essentially recovers the tracking efficiency, but it makes it harder for the GNN. So currently the best results that I have to show tracking wise are from Edge Classifier 2, and we have the PT at 2 GeV, and we get about 94% tracking efficiency and very small frake rates of about 0.1%. And the GNN is about 99%. The Edge Classifier 2 is 99% effective roughly at selecting tracks. And so now I'll go on to some ongoing work. So as I mentioned, we're converting all the code into like this usable framework, which is the PyTorch geometric. So we have all the graph construction code, Edge Classifier 2, and the union find tracking code is all there. Edge Classifier 1 is partially converted, and then I think one of the only other things left to convert is probably the interaction network. And then we want to continue optimizing cuts, because I'm sure as we start to look at other architectures, we'll find that cuts that are optimized for Edge Classifier 2 might not necessarily be optimized for like the interaction network or whatever. And then we definitely want to look at more architectures. So I think we've very recently started looking at like one-shot clustering techniques and different ideas. Is there any more data augmentation tricks that could be used? Any transforms or embeddings that we could use? And then we definitely need to do more in the track building side, because the track building is very rudimentary at this point, and we want to look at different algorithms. So in summary, the GNNs are pretty promising, a very promising method for the HL-LHC tracking. Geometric data representation with variable number of inputs. We've looked at a variety of architectures, and we have seen that they work. The focus now is just kind of optimizing them and then trying to reduce graph size as much as you can while preserving that performance so that you can potentially put it in a FPGA. The graph construction is very critical to performance. Almost, I mean, you can invert like the coordinates or something and totally wipe out like all your results just from doing some weird cut in your graph. And so, we're working towards accelerating all this on FPGAs, which Javier will talk about next. Thank you.
Thanks, Marcus. If anyone has questions, please feel free to just unmute yourself and ask, so we can do a few minutes of questions before switching to Javier's talk.
Marcus, as far as other transforms, I know at one point we were kicking around the thinking of how to meld the Huff transform with GNNs, but do you remember if we had any conclusions there or what your thoughts?
I mean, we definitely tossed around the idea. I don't think we've ever concluded much. I don't think we've.
Okay, so
I don't think we've gotten to the point where we've even really looked at it all that much.
Yeah, that's something maybe to explore. Okay, thanks.
Yeah.
Any other questions for Markus? Okay, thanks, Markus. So if you can stop screen sharing, we can switch to Javier's talk on the acceleration with FPGAs.
Thank you.
Okay, can you guys see and hear me?
Yep.
Okay.
The slides are not full screen if you wanted. Oh, okay, great. Yeah.
Oh, okay. Great. Thanks. So yeah, thank you, Markus and Savannah. So as they said, I'll be talking about accelerating GNN tracking on FPGAs and talking about the preliminary work we've done so far. And specifically, I'll present on the behalf of many others, including people on this slide, and specifically including 2 IRIS-HEP fellows from the summer, Anish Heinz and Vessel. So to first introduce the topic, I mean, it's already been introduced, but briefly, so GNN tracking may be able to scale better than traditional tracking algorithms and may be more easily parallelized on heterogeneous computing resources like FPGAs. And so we've actually done some previous work, which you can see at this archive link, in which we implemented simple GNNs on FPGAs for high energy physics, and specifically for the task of particle energy regression. So in this talk, I'll be talking about 2 sort of complementary FPGA implementations of GNN-based segment classifiers using HLS for ML and OpenCL. So 2 sort of open source frameworks that I'll talk about. So first, maybe I should just remind you of what to put them on an FPGA, I should remind you of what operations we actually need to then put on the FPGA. And so neural network operations, the sort of atomic unit is this, is the equation you see here. So it's basically composed of 3 pieces. One is a multiplication of a weight matrix by an input data vector. The other is an addition of a bias vector. And then finally, there's the application of a nonlinear activation function. And what's nice is that these sort of basic operations all map nicely onto different FPGA resources. And you can actually trade off which ones you use for which operation. So typically use the DSPs, which are special blocks for the multiplications, and the lookup tables or LUTs for the addition and the activation function. But sometimes you can actually swap these things around. So in general, FPGAs are these programmable hardware chips, which have this nice feature that you basically have these embedded components like these DSP slices, which can perform multiplications, and then these LUTs that can apply arbitrary logic functions, as well as these block RAM units that can store memory. And these are all embedded components throughout the chip. And then there's reprogrammable interconnects. So you can think of them as just like, before you program it, they're just a clean slate where you can have any of these pieces connected, well, not any, but a large fraction of these different components connected to each other. And then when you program it, you basically, choose which, parts of these interconnect highway you actually activate. And there's also high throughput connections going off of the chip to, for example, other FPGAs. So this is useful for sort of putting, for example, models on multiple FPGAs or communicating with upstream or downstream processing. In general, they're relatively low power, at least compared to CPUs and GPUs, although not necessarily compared to ASICs. One con, however, is of course that up until recently, it usually requires a lot of domain knowledge or electrical engineering expertise to program, specifically using RTL languages like VHDL or Verilog. Okay, so then if you're thinking about putting neural networks on FPGAs, there's actually several handles that you have in terms of making the models themselves more efficient. So one is this general idea of compressing the model. So the simplest thing you can do is actually just make it a smaller model. So use less nodes per layer or less number of layers in total. Another handle you can use is actually start with a big model and actually prune away redundant connections. And this actually can be very effective and actually keep the high performance without as much resources. The other handle you have, which is kind of a necessary fact of reality when moving to the FPGA, is you typically want to quantize the model in the sense of using reduced precision for all the computations of these, for example, for the weights and activations that you compute. So in this case, we chose to actually just look at post-training quantization, which is where you reduce the precision of a pre-trained model, where the model is trained in 32-bit floating point, and you just reduce it to something like, for example, 16-bit fixed point representation for running on the FPGA. And what we find is, in general, as long as you have enough bits, that this post-training quantization actually works pretty well, and again, lets you reduce the number of bits you need for the computation. A sort of new technique that we've been exploring more recently is called quantization-aware training. And what this means is that you actually clip the weights and activations during a forward pass of the training, but actually not during the backward pass. And this is actually to maintain stability because these are, as you can imagine, if you do this also during the backward pass, you actually can destabilize the training. And this is effectively has been shown to emulate quantization very, very effectively. And then when you quantize, of course, you're basically still applying the same clipping procedure. You're effectively doing the same thing when you quantize. So it ends up giving you a model that's still very effective in this reduced precision. And what we found is with this quantization-aware training, you can actually usually achieve much lower precision. So something like 6-bit, 4-bit, or even ternary or binary operations can reproduce the performance of a full 32-bit floating point model. And finally, sort of the third handle you have, which is more specific to the FPGA architecture, is balancing parallelization, so how fast you want the result, with the resources needed, so how costly it is to run the algorithm. And this in general, which I'll talk about in the HLS for ML implementation, we usually quantify with sort of this concept of a reuse factor, which is sometimes interchangeable with an initiation interval, which is how long you have to wait before an algorithm can accept a new set of inputs. So what this little diagram on the right shows is the difference between a reuse factor of 1 on the bottom, in which you assign a resource to do every single one of the multiplications in parallel, versus a reuse factor of 4, for instance, where you actually reuse the same multiplier unit 4 times. And so then you're actually having to wait, for instance, in this case, if you were going to do another one of these computations, you'd have to wait 4 clock cycles before you could then reuse that same multiplication unit. Okay, so then now more to the specifics of this task. We used very much the same setup as the previous talk. So using this Kaggle TrackML dataset, where the hits are encoded as the nodes of the graph, plausible track segments are encoded as the edges of the graph initially, and then the targets of the learning problem are trying to assign or basically classify good track segments, which actually connect 2 nodes that are part of the same track. And so those are our edge classification targets. And so shown here are full event graphs of the inner layers of the detector for these layers shown here. And this is with a specific PT cut of 2 GeV and some other geometrical requirements. And in the end, we end up with a graph that contains roughly 1,000 nodes and 1,500 edges. And for the HLS for ML implementation, as I'll discuss in a bit, we actually segment this further in Eta and Phi to sort of look at this, sort of start with smaller models and smaller graph sizes. Okay, so with this in mind, we can talk a little bit about the one of the frameworks we use, so HLS for ML. And what this is it's basically a tool for physicists or machine learning experts to translate machine learning algorithms into FPGA firmware. So the way that it works is you have the usual machine learning software workflow where you can train a model in Keras, TensorFlow, or PyTorch. And then the HLS for ML library basically automatically converts a model specified in some serialized format. It could be JSON or it could be, H5 format of one of these libraries. And it converts that into an HLS project automatically using templates for the basic building blocks and putting them in the right order. Once you have this HLS project, you can actually further tune it by hand if you're interested. So changing things like the precision or the reuse factor or the pipelining. And but you also have handles to do this within the HLS for ML library. And then after you've done this step, you sort of leave the HLS for ML library, and then you enter it usually into some vendor specific tools. So for example, for Xilinx FPGAs, there's Vivado HLS or Vitis HLS, which then converts that HLS project into a FPGA firmware based, RTL, for example, as well as the actual bit file that you can then run on an FPGA. Okay, so the HLS for ML model. So the model that we started with was essentially modeled after a previous segment classifier shown at the NeurIPS 2019 Machine Learning for Physical Sciences workshop, and there's an archive link to explaining that specific model. However, in order to sort of test, be able to iterate faster in terms of testing an FPGA implementation, we actually did some simplifications. So first simplification was we reduced sort of the latent size that was used for the representation of the edges and nodes. In this case, for example, the encoder transforms the node and edge features into an 8-dimensional latent space. Afterward, the edge block essentially computes messages, which are updated edge features between the nodes. And then the node block subsequently updates node features based on these messages. Sorry, it should say based on these messages. The decoder then essentially transforms the edge features, this 8-dimensional latent space, back into an edge weight classifier. So it gives you one number per edge, which is between 0 and 1, and it essentially is classifying the edges as good or not. So this interaction network module could actually be iterated when it was in this original model. But for now, we kept one iteration, although this is tunable. You can change this in the implementation. And we also kept a small latent space in order, again, to keep the model small. Okay, so then the actual implementation I linked here. So I just wanted to point out a couple things about it specifically. So one thing is that we use the way you encode the data is very important. So here, the way we encode the graph connectivity is using 2 arrays of receivers and senders, which basically index which nodes are connected to one another. So we actually use those as input to the FPGA algorithm and use those to dynamically index which parts of the node feature matrix need to be grabbed and then run a neural network on together. So that's actually one very difficult part of the FPGA implementation, is that right now this is probably one of the most resource consuming parts because you need to dynamically index things. And in general with FPGAs, you want to know as much as you can before you compile it. So in this case, we're compiling something where it knows it needs to dynamically index something, and that's actually a very difficult step for it. So we have ideas actually related to things like pre-processing the graph in a certain way, which might actually help reduce the resources quite a bit. The other aspect I wanted to point out is that we, in general, again, for FPGAs with a fixed, you want to have a fixed latency and a fixed, basically a fixed latency. What this means is you want to have a fixed graph size because you're doing a certain number of operations per node and per edge. So if you don't have a fixed number of nodes and edges, you're going to have a variable latency. And while this might be okay for co-processing applications, for more real-time applications like in the trigger, you really need that fixed latency. So in order to achieve that, we actually do zero padding up to a set maximum graph size, which we choose based on the input data. So we look at the input data and we say, okay, the 95% percentile of the graph sizes is this. So, we make sure we're not truncating 95%, let's say, of the input data. And this is sort of, again, just a trick to make sure we have a fixed graph size so that we have a fixed latency. Finally, yeah, so then we also pipeline with a certain initiation interval, which in this case is equal to the reuse factor at the edge and block and node block level. Okay, so that's probably too much detail, but I can show you what the results look like for this, this implementation. And again, to sort of iterate faster. Oh, actually, I'm missing one slide, but that's okay. I wanted to show one slide on how much the accuracy or the AUC, sort of the performance metric, depends on the total bit precision. And what we find is with 12 bits of precision, the model already reproduces the 32-bit floating point model. So in that sense, we only need 12 bits, but nonetheless, we show scans of the bit precision just so that you can get an idea of how the resources depend on that choice. And again, to iterate faster, we actually are showing results for 1/64th of a detector. So this is a fixed graph size of up to 28 nodes and 37 edges. And what you see here is that the HLS for ML implementation actually on the right has a latency of less than 1 microsecond. So this is a 5 nanoseconds clock cycle. And you can see it, from 10 to 20 bit total bits, it scales from about 130 to about 180 clock cycles. So again, all of it is less than 1 microsecond, which is about 200 clock cycles. And then on the left, you're seeing the total resource usage on the FPGA of the different components. So you can see the DSPs, our usage is actually pretty low. It's around, it caps out about 50%. The largest resource that you see here is the LUTs. But we actually should note that the LUTs are almost always overestimated in the HLS estimates, which is what we're seeing here. And so that should very well go down during the actual implementation phase. And moreover, there might be some other tricks we can do to actually reduce that. Then we also scanned this same model with the reuse factor to see how we can essentially reduce the resources that way. And then again, here you see, and I should say the previous scan was done with a reuse factor of 8. So that's the specific reuse factor that was used here. And then if we also scan the reuse factor, you can see that as you go to higher reuse factor, in general, the resources go down. So you can use that as a handle to reduce the resource consumption, especially for the DSPs. And then on the right, you can see that as expected, the latency does grow with the reuse factor because you're trading area on the FPGA for time. And so here you can see it does grow and kind of gets up to just above a microsecond. Okay, so that's about the first implementation. So I'm kind of switching gears now to talk about the second implementation. And that's based on this OpenCL language, which is a sort of platform agnostic framework for writing programs that can potentially execute across heterogeneous platforms like CPUs, GPUs, and FPGAs. So the way that it works is it assumes this paradigm that there's a host CPU that talks to the heterogeneous resource and runs kernels that are accelerated on that resource. And then there's a bunch of methods that you can use to try to improve the efficiency. So for instance, one of them that I'll mention is this idea of double buffering, which allows essentially the host to do processing and usually it's the big thing is transferring data while the kernel executes on the current batch of data concurrently. And so this actually allows you to reduce the resources because you're able to basically keep the kernel running continuously rather than having a gap where you're waiting for the host to process data and then to transfer it. And all of this is tested on an ARIA 10 GX 1150 FPGA, and I should actually mention the previous study was done on a Xilinx, or targeting a Xilinx KU115 FPGA, and both of those are actually pretty similar in terms of they're good for comparing against each other. Okay, and then the other thing I should note is that actually, we're using a different model for the OpenCL implementation, although this is something we're looking to fix in the sense of being able to benchmark the two implementations against each other. But nonetheless, the OpenCL model actually looks like this. So it iterates, there's no encoder and decoder step, and it uses the edge block twice. So it has an edge block, which goes into a node block, and then an edge block again, which then gives you the edge weights. And so the other big difference is that this is actually a much larger model in terms of the latent space. So you can see that for the edge features, there's 250 dimensional latent space. For the node features, there's a 200 dimensional latent space. So that's another big difference. So for this model implemented with OpenCL, you can see that it, in general, is able to scale up more easily to larger graph sizes. So in this case, you're seeing on the right that the latency as a function of the minimum PT cut, and the minimum PT cut, the number of nodes and edges depends very strongly on the minimum PT cut. So it goes down to 1 GeV, which is a much larger graph size than we've looked at with the HLS for ML implementation. And conversely, the latency is also much longer. But this is sort of to be expected, because in this case, we're actually taking into account not only the FPGA time, but also the time for transferring the data from the CPU and then back again. Nonetheless, actually, the resources usage is actually quite manageable on the FPGA. So this is, again, showing you a trade-off of using longer processing time can give you less resources. Okay, so to summarize, so I've shown sort of two complementary implementations of the GNNs on FPGAs. The current performance seems to be promising both for potentially trigger level applications with the HLS for ML1, and also co-processing applications, which might be possible with both of the OpenCL and HLS for ML implementations. The OpenCL implementation is able to scale more easily to larger graphs and also larger models. But the HLS for implementation does have a latency or throughput advantage. So for future work, we're looking to extend and scale up both of these implementations to make them more flexible and be able to test different types of GNNs, especially as you saw in the previous talk, there's lots of development on the architecture side. And then also benchmark the two implementations against each other using the same architectures. So thank you.
Thank you, Javier. Are there any questions?
Maybe just a quick comment that I would just like to say, you know, if I compare where we were months ago to now, I mean, the IRIS-HEP fellows really drove forward on this for our group. So I think that should really be noted, that was a great spark and they did a great job.
Yeah, definitely. Any other questions or comments? Okay, well, thank you, Javier. I guess we can close the meeting for now. And yeah, we appreciate everyone joining in. Thanks to both our speakers. Have a great day, everyone.
Thank you.
Thank you.
Bye.
Okay.